Okay, so welcome back. This is lecture 18. In this lecture, we'll look at some applications that involve eigenvalues, eigenvectors, and the SVD. So the first application we'll look at is statistics. So we'll go through an example of a statistics problem that involves linear algebra. So we're going to start with a matrix that contains some data from the real world. Call it a matrix of observations. Okay. So if A is an m by n matrix of observations, this means it contains n many samples over m many variables. Okay. So there are n many observations, and what they're describing is two variables. Okay, so for example, if this was the matrix of observations, it could be that the first variable describes ages, and the second variable describes the weight of, let's say, 6 different cats. Okay, so this is a matrix of data. So before we analyze this data, we have to center it. Okay. So if you do a scatter plot of this data, right, it'll be a bunch of points in the top right quadrants. Okay. To analyze it, we want to center it. That means we want to move it to the center of the graph so that the average is the origin. And we'll see a graph of this later. So how do we center the data? Okay, so it's a straightforward process. What we want to do is compute the average or the mean of the first row, and then subtract the average off of every entry in the first row. And then do the same for the second row. Compute the average and then subtract the average off of each entry in the second row. Okay, so the first row has average 4, if you compute it. Second row has average 9. Okay, so I subtract 4 from every entry in the first row, subtract 9 from every entry in the second row, and this is my result. Okay, it's a different matrix. I'll call it B. And this is called the mean deviation form of the data. So when you have a set of data, two important numbers that are attached to that data is the variance and the covariance. Okay, so for each variable, there's a variance to it, right? And the variance describes how much that variable varies. In other words, what's the spread of the variable? Is it all packed together around one number, or is it spread out? Okay. The covariance tells you the relationship between two variables. Okay. So if you have a large positive number, then that means the two variables are strongly correlated. Okay, there's a strong relationship between the variables. Okay, so to easily read off these numbers, what we do is form the sample covariance matrix. We're going to call that matrix S. And how we do this is we look at our centered mean deviation form of the data, B. We compute B times B transpose as a matrix. And to get the statistically correct scale, we have to divide by 1 over n minus 1, okay, where n is the number of samples or the number of columns of B. Okay. Once we've done this, we can read off the variances and the covariances. The variances will be the diagonal entries of S, and the covariances will be the off-diagonal entries of S. So we do that for our data set. We get S. Then we want to divide by 1 over 6 minus 1, or 1 over 5. And this is the result of computing B times B transpose. And then we compute this just by bringing in the 1 over 5 like this. And this is our sample covariance matrix for the data set B. Notice it's symmetric, right? We know matrices of this form are always symmetric, right? And so the variance of the first variable will be 5.6. So the variance in the age, if we interpret that as the age, and the variance in the second variable will be 18. Okay. The 8 here on the off diagonal describes the covariance between the first variable and the second variable. So we have a positive number here, and so that means there's some correlation between the first and second variable. And that makes sense. Something that's older should weigh more. Right? So now we'll talk about the principal components of a data set. Okay, so the principal components of a data set are the unit eigenvectors of the sample covariance matrix S. Okay, so for our example of this S here, you can compute that the first eigenvalue, that is the largest eigenvalue, is this number, and the second eigenvalue, the lesser eigenvalue, is this number. Okay, so we want to order them in descending order. We can also compute that the unit vector corresponding to the biggest eigenvalue is this, and the unit vector corresponding to the second biggest eigenvalue is this. Okay, you can see they're sort of opposites of one another in that they're orthogonal, which is what we're expecting, right? Since S is a symmetric matrix, that means its eigenvectors are going to be orthogonal, like this. Okay. So U1 is called the first principal component, since it's the eigenvector with the largest eigenvalue. So what the first principal component, U1, is describing is the direction of greatest variance. Okay, so over here, in the green dots are the points in B, okay, or the observations in B. Right? So you can see they're all centered around the origin now. Okay, and this purple dot is the first principal component. Okay, so along this axis is where the greatest variance is. Okay, so if I were to fit an ellipse to these points B, then what this vector is describing is the direction of greatest deformity, right? So it's related to the SVD, right? Based on the previous observation, this vector describes the first right singular vector of B. In other words, U1. Okay? So if you check, you'll see that the right singular vectors of B are the eigenvectors of S. Okay. So we can compute the principal components by computing the U's of B instead of the eigenvectors of S, because they're the same thing. Okay? So before, when we were discussing the geometry of the SVD, we had a matrix, and that matrix deformed R2, and we tracked how it changed the unit circle, and it changed it into an ellipse, and our right singular vector pointed in the direction of greatest change, or greatest variance. Okay, so in this case, in the statistics case, it's a similar sort of idea, right? But we're given a different input. Now we're given a set of data, and then we want to fit an ellipse to that data and ask, what's the deformation that caused this? Okay, and so we look for the singular vector that points in the direction of greatest deformation, which is our U1. So in conclusion, computing the eigenvectors of S or computing the right singular vectors, or the U's of B, the data set, will give you the same vectors. Okay, but it turns out for large data sets, computing the SVD of B is a lot faster and more accurate than computing the eigenvectors of S. Okay, so now I'll talk about the total variance of a data set. So what is the total variance of a data set? Okay, so if we look at the matrix S, we know that the variance of the first variable is on the first diagonal spot, and the variance of the second variable is on the second diagonal spot. Okay, so in general, the total variance, the sum of all the variances, will be the sum of the diagonals, right? Okay, so the total variance is equal to the trace of S, where the trace of a matrix is the sum of its diagonal entries. So now we're going to use a fact that we haven't mentioned in this class yet, but is quite useful. The trace of any square matrix is equal to the sum of its eigenvalues. Okay, so if we combine this fact with this fact, this tells us that the total variance of a data set is the sum of the eigenvalues of S, right? So each principal component describes a certain amount of the variance. Okay, the first principal component describes the most amount of the variance. The second principal component, which would be in this direction, describes the second most amount of variance. And if you're to sum them all up, they describe all the variance. Okay, so knowing what we know about total variance and the eigenvalues of S, we know how much each principal component contributes to the total variance. Okay, so we can ask that question of our sample here. Okay, so the fraction of the total variance contained in the first principal component, U1, will be lambda 1, its eigenvalue, divided by the sum of all the eigenvalues, the trace of S. Okay, so I take the sum of all the eigenvalues, so this is just lambda 1 plus lambda 2, and this is lambda 1 on top, and I see that 92.8% of the variance is contained in the first principal component. So now we'll move on to a different application. Okay, we'll look at data compression and image compression. Okay, so let's suppose I have this image here. Okay, so this is a flag of the Netherlands. Okay, so let's suppose I wanted to store it as a computer file, store it as a matrix or an array. Okay, so what I can do is just sort of look at each pixel and describe its color by a number. So I'll have all reds in the first two rows, all whites in the third and the fourth row, and all blues in the last two rows, right? So like in an actual matrix, I wouldn't put in R, I would put in a number representing R. Okay? So it's believable that you can store an image as a matrix on a computer. So how much space does this matrix take up, approximately? So I have 6 rows and 6 columns. So if I record this just by writing down each color, then this will take up about 36 units of storage. Okay? But there's a lot of repetition here, right? So I should be able to store this in a more effective way, right? And that's where compression comes in. Okay? So I notice that since there's so much repetition, I can factor this matrix like this into 2 different matrices, right? And then just store these 2 different matrices. How much storage will that take up? Well, 6 entries here, 6 entries here. Only 12 units of storage, right? Okay, so this is an effective compression. Okay. Instead of storing all this, I just compress it, store these 2 matrices, and then make a note that to decompress this information, multiply the matrices, and you'll get back the original file. Right? So notice that this is a rank 1 matrix, right? Every column is, a repeat of the first column. Okay? So rank 1 matrices are easy and effective to compress. So what about a bigger matrix? Okay. So here we're going to show that factoring a matrix can often allow for compression. Suppose we have a 500 by 500 matrix A. So you can imagine it as an image that's 500 by 500 pixels. Okay. So uncompressed, this takes up about 500 times 500, in other words, 250,000 units of data. Okay. So let's suppose that A has a relatively low rank compared to its size. Okay, so let's say that the rank is 50. Okay, so if the rank is 50 and I do the CR factorization on A, it'll look like this. Okay, so since the rank is 50, we have 50 columns in the basis for the column space. Okay, so our C matrix will be 500 times 50. And our R matrix, which is the reduced row echelon form, but with the zeros deleted, okay, will be a 50 times 500 matrix. Okay, so if we look at how many entries are in each matrix, there'll be 50 times 500 and also 50 times 500. And if we sum up, there'll be 50,000 entries in total that we have to store. Okay, so if we compress this by factoring it like this into 2 matrices, we only take up 50,000 units of data compared to 250,000 units of data it would take up uncompressed. Okay, so that's a large factor of compression, right? It's a 1/5 the storage space. Right? If you have a matrix with a low rank compared to its size. So if you have a large matrix with low rank, that means there's a lot of dependence between the rows and the columns. And that means you can compress it effectively. Okay. So here's another example of compression by factorization. So we'll use the same A, a 500 by 500, with rank 50. This time we'll use the pieces of the SVD. Okay. So again, this is 250,000 units uncompressed. If we look at the pieces of the SVD, since the rank is 50, we'll have 50 pieces, right? So how big is each piece? Okay. So the sigma is just a number, so it's a 1 by 1, so it's just one piece or one entry. Both U1 and V1 are vectors with 500 entries in them. Okay. So each piece is going to have 1 plus 500 plus 500 units of data. Right? And so the whole thing together is going to be a little over 50,000 units of data compressed with the SVD. So it's basically the same as the CR factorization, right? Okay, so these two examples we just showed are with matrices that have very low rank compared to their size. Okay, most data that you get from the real world or from an image will not have low rank. Okay, they'll have very high rank. So, if you take a picture and it's 500 by 500 pixels, the rank of that matrix that stores the image is going to be 500. Okay, right. If you take a picture in the real world, there's almost no chance that a row of the image is going to be exactly the same as another row or some linear combination of another row, right? It just doesn't happen, right? So for that kind of data, these compression techniques won't work. Okay. At worst, they can take up more space if you apply it blindly. Okay. So now we want to use our low rank approximations to compress our data. Okay. So for every matrix, we can get the SVD, and we can get the pieces of the SVD like this. Okay. And our low rank approximation by the Eckart-Young theorem told us that the pieces come in order of importance. In other words, the piece attached to sigma 1, which is the biggest of the sigmas, is the most important, and the piece attached to sigma r is the least important. Okay? And the importance goes down as you move this way, right? It's ranked by importance. Okay, so suppose you have a matrix A and it has full rank. Like suppose it's a 500 by 500 and the rank is 500. Okay? So that's a lot of pieces. Okay? Each piece takes up an equal amount of storage space, but the first pieces more to the left, contain most of the essential information. Okay? So the idea of compression via low rank approximation is that by omitting the less important pieces, you can save a large amount of storage space, but only lose a small amount of information. Okay, so if R is 500, I can just forget about the trailing 250 pieces. Okay, so the last 250 pieces, and just keep the first 250 pieces. That will take up half the storage space, but it will have more than half of the information. Okay, so we can see this visually with image compression. Okay, and we'll see a demo of this now. Okay, so we can see image or data compression using low rank approximations visually. Okay, so here is a tool that allows you to see this. So we've uploaded an image that's 800 by 633 pixels. So it's an 800 by 633 matrix. So that means its rank will be 633. So in its singular value decomposition, where we write it as a sum of pieces, there will be 633 pieces ranked in order of importance. Okay, so this tool allows me to see what it looks like when I just include the first piece, what it looks like when I include the first 10 pieces, the first 20, first 100, and so on. Okay, so this image has 633 pieces, and right now we're looking at just the first piece. Okay, the rank 1 matrix that's closest to the full matrix. Okay? And it doesn't look like anything, right? It's just a bunch of lines. Okay, but we can sort of see that it is a rank 1 matrix because all the columns are straight lines and all the rows are straight lines. So let's add another singular value. So take the sum of the first 2 pieces. Okay, so our image is starting to form now. 3 pieces, more detail, 4, 5, 6. Now that it's up to 10, you may be able to guess what this image is. Okay, go up to 20. Right? If we go up to 100, and it's this Starry Night painting, right? Okay, so if I only include the first 100 pieces of the SVD, I get this much of the picture. This is the whole picture. Right? This is the complete uncompressed picture you're looking at now. But if I just store the first 100, it looks like this. Okay? It's slightly blurry, but you can still tell what it is, right? If I go up to, say, 200, then it looks identical to the full image. Right? This is the full image, and this is just the first 200 pieces. They look basically identical to the eye. So all the essential information is being stored in like these first 150 singular values, right? And the singular values past that are the less important pieces, and they just add like small, fine details. Okay. So for the Starry Night picture, I needed about 150, 200 pieces or singular values to get a good looking version of the image. Okay. What the image is, or what the data is, can affect how well it can be compressed. Okay, so if we look at this image here, this is the full uncompressed image. So it's 640 by 635. So it will have a rank of 635. Okay. but this is a very blocky image with lines on it, right? So our expectation is that it should be able to compress more easily than the previous image, which had a lot of little details and a lot of curvy lines in it. And so let's try that out. So this is the full image. Okay, so what does it look like with just one singular value? Okay, sorry, this is what it looks like with one singular value. Okay, and how many singular values do we need? How many pieces do we need so that it becomes recognizable? Okay, so just at around 10, we start to see its original form. And around 20, it starts to look pretty much like the original. Okay, so when I hover over, it restores the original. So this is the original. Okay, we can see there's a lot of specks of dust here, and the signature here at the bottom, they don't show up on the 20-piece version. Right, this is the 20-piece version, and this is the original. See how the signature changes? You lose some of the dust, right? If we add up some more singular values, at around 50, the signature appears quite well. It's just a little bit of dust we're missing, right? If we go all the way to 100, it becomes virtually identical to the full image. Okay, so this image, which has a lot of lines and a lot of blocks, a lot of repetition to it, can be more effectively compressed, right? We don't need to add that many pieces to get an image that looks very close to it, right?